Hydraulic pumps are used in hydraulic drive systems and can be hydrostatic or hydrodynamic. A hydraulic pump is a mechanical source of power that converts mechanical power into hydraulic energy. It generates flow with enough power to overcome pressure induced by the load at the pump outlet. When a hydraulic pump operates, creates a vacuum at the pump inlet, which forces liquid from the reservoir into the inlet line to the pump and by mechanical action delivers this liquid to the pump outlet and forces it into the hydraulic system. Hydrostatic pumps are positive displacement pumps while hydrodynamic pumps can be fixed displacement pumps, in which the displacement cannot be adjusted, or variable displacement pumps, which have a more complicated construction that allows the displacement to be adjusted. Although, hydrodynamic pumps are more frequent in day-to-day life. Hydrostatics pump, which are of various types, works on the principle of Pascal's law. It states that the increase in pressure at one point of the enclosed liquid in equilibrium of rest is transmitted equally to all other points of the liquid, unless the effect of gravity is neglected. In case of statics, hydraulic pump types, gear pumps are simple and economical pumps. The swept volume or displacement of gear pumps for hydraulics will be between about 1 and 200 milliliters. They have the lowest volumetric efficiency of all three basic pump types. These pumps create pressure through the meshing of the gear teeth, which forces fluid around the gears to pressurize the outlet side. For lubrication, the gear pump uses a small amount of oil from the pressurized side of the gears, leads this through the hydrodynamic bearings, and vents the same oil either to the low-pressure side of the gears, or through a dedicated drain port on the pump housing. Some gear pumps can be quite noisy, compared to other types, but modern gear pumps are highly reliable and much quieter than older models. This is in part due to designs incorporating split gears, helical gear teeth and higher precision quality tooth profiles that mesh and unmesh more smoothly, reducing pressure ripple and related detrimental problems. Another positive attribute of the gear pump is that catastrophic breakdown is a lot less common than in most other types of hydraulic pumps. This is because the gears gradually wear down the housing and/or main bushings, reducing the volumetric efficiency of the pump gradually until it is all but useless. This often happens long before wear causes the unit to seize or break down. Rotary vane pumps have higher efficiencies than gear pumps, but are also used for mid-pressures up to 180 bar in general. Modern units can exceed 300 bar in continuous operation, although vane pumps are not regarded as high-pressure components. Some types of vane pumps can change the center of the vane body, so that a simple adjustable pump is obtained. These adjustable vane pumps are in general constant pressure or constant power pumps. The displacement is increased until the required pressure or power is reached, and subsequently the displacement or swept volume is decreased until an equilibrium is reached. A critical element in vane pump design is how the vanes are pushed into contact with the pump housing, and how the vane tips are machined at this very point. Several types of lip designs are used, and the main objective is to provide a tight seal between the inside of the housing and the vane, and at the same time to minimize wear and metal-to-metal contact. Forcing the vane out of the rotating center and towards the pump housing is accomplished using spring-loaded vanes, or more traditionally, vanes loaded hydrodynamically. Screw pumps consist of two Archimedes screws that intermesh and are enclosed within the same chamber. These pumps are used for high flows at relatively low pressure. They were used on board ships where a constant pressure hydraulic system extended through the whole ship, especially to control ball valves but also to help drive the steering gear and other systems. The advantage of the screw pumps is the low sound level of these pumps. However, the efficiency is not high. The major problem of screw pumps is that the hydraulic reaction force is transmitted in a direction that's axially opposed to the direction of the flow. There are two ways to overcome this problem: 1. Put a thrust bearing beneath each rotor. 2. Create a hydraulic balance by directing a hydraulic force to a piston under the rotor. Types of screw pumps: 1. Single end, 2. Double end, 3. Single rotor, 4. Multi-rotor timed, 5. Multi-rotor untimed. Bent axis pumps, axial piston pumps and motors using the bent axis principle, fixed or adjustable displacement, exists in two different basic designs. The Thoma principle with max 25 degrees angle and the Woolmark principle with spherical-shaped pistons in one piece with a piston rod, piston rings, and maximum 40 degrees between the drive shaft centerline and pistons. These have the best efficiency of all pumps. Although in general the largest displacements are approximately 1 liter per revolution, if necessary a 2-liter swept volume pump can be built. Often variable displacement pumps are used, so that the oil flow can be adjusted carefully. These pumps can in general work with a working pressure of up to 350 euro 420 bars in continuous work. Inline axial piston pumps, swash plate principle. Axial piston pumps using the swash plate principle have a quality that is almost the same as the bent axis model. They have the advantage of being more compact in design and also allow use of through-drive series-mounted auxiliary rotating equipment, based on their inline design. The pumps are easier and more economical to manufacture. The disadvantage is that they are more sensitive to oil contamination. The axial piston pump is likely the most widely used variable displacement type, being found in everything from heavy industrial to mobile applications. By using different compensation techniques, the variable displacement type of these pumps can continuously alter fluid discharge per revolution and system pressure based on load requirements, maximum pressure cutoff settings, horsepower ratio control, and even fully electroproportional systems, requiring no other input than electrical signals. This makes them potentially hugely power-saving compared to other constant-flow pumps and systems where prime-mover electric motor rotational speed is constant and required fluid flow is non-constant. Radial piston pumps. Radial piston pumps are used especially for high pressure and relatively small flows. Pressures of up to 650 bar are normal. In fact, variable displacement is possible. The pump is designed in such a way that the plungers are connected to a floating ring. This floating ring can be moved horizontally by a control lever and thus causes an eccentricity in the center of rotation of the plungers. The amount of eccentricity can be controlled to vary the discharge. The suction and discharge can be totally reversed seamlessly by shifting the eccentricity to the opposite side. Hence both quantity and direction can be varied in a radial piston pump, just as in the swash plate pump. Peristaltic pumps. Peristaltic pumps are not generally used for high pressures. Pumps for open and closed systems. Most pumps are working in open systems. The pump draws oil from a reservoir at atmospheric pressure. It is very important that there is no cavitation at the suction side of the pump. For this reason the connection of the suction side of the pump is larger in diameter than the connection of the pressure side. In case of the use of multi-pump assemblies, the suction connection of the pump is often combined. It is preferred to have free flow to the pump. The body of the pump is often in open connection with the suction side of the pump. In case of a closed system, both sides of the pump can be at high pressure. The reservoir is often pressurized with 6 to 20 bars boost pressure. For closed-loop systems, normally axial piston pumps are used. Because both sides are pressurized, the body of the pump needs a separate leakage connection. Multi-pump assembly. In a hydraulic installation, one pump can serve several cylinders and motors. However, in that case a constant pressure system is required and the system always needs full power. It is more economic to give each cylinder and motor its own pump. In that case, multi-pump assemblies can be used. Gear pumps are often supplied as multi-pumps. The different chambers are mounted in one body or built together. Vane pumps and gerotor pumps too are often available as multi-pumps. Screw pumps can be combined with gear or vane pumps. Axial piston swash plate pumps can be combined with a second pump, or with one or more gear pumps or vane pumps. Axial plunger pumps of the bent axis design cannot be combined with other pumps. Hydraulic pumps. Calculation formulas. Flow. Wear. Power. Wear. Mechanical efficiency. Wear. Hydraulic efficiency. Wear. References: Parr, Andrew. Hydraulics and Pneumatics: A Technician's and Engineer's Guide, pages 38. Elsevier. External links: external gear pump description, internal gear pump description, mechanical efficiency description, hydraulic efficiency description. See also, vane pump.